So good evening everyone. Yeah. So what we discussed in the last class, tell me, anyone here? The periodic properties, atomic radius, ionic radius, okay, and then next we have also discussed about ionization energy, okay. I just wanted to go through the last class with this one question. So tell me, how can you answer this question for the given question? Which of the following options represents the ionic radius of these three anions? Tell me. Option 3. Why option 3? Because more the negative charge, see all of them are having 10 electrons in them right now. So more the negative charge, more is the electron expansion, cloud expansion, so bigger will be the size. So this will be maximum, so that is there in this option 3, and after that O minus to S. So 3 option. Next we discussed about ionization energy. So just look into it, what exactly ionization energy means. Anyone can tell me? The minimum amount of energy required to remove the electron from neutral gaseous isolated atom, okay. So if A is an atom, from this consider it is an isolated atom which is in gaseous state. If this is not in gaseous state, first convert into gaseous state, then only you can consider it as ionization energy, okay. So from here you need to make it ionize. It means you need to remove electron from here. It becomes a cation like this right now, unipositive cation. The minimum amount of energy you are using for picking out this one electron is called its ionization energy. This electron comes from the valency shell of this atom, okay. That is clear now? Yeah. So now if I remove one more electron from here, it will become A plus 2 right now. So you should call this as IE1 and this is IE2 like this. If I remove one more electron, IE3. So like that we have successive ionization energy. Always remember, as positive charge increases on that ion, cation, it is very difficult to remove the electron. Therefore successive ionization energy increases. So like IE3 will be greater than IE2, greater than IE1 like this, okay. It's so on, okay. Always remember. Now what I told you, ionization energy, during that we will remove electron from valency, okay. So now if the atom strongly hold that electron, it requires higher energy right now. If it is loosely bounded, lower energy is required, less energy is required to pick out that electron, okay. So now for the elements, now we will discuss the applications. Yesterday only we have discussed this thing, okay. So now tell me how the trends in the periodic table, how this ionization trend changes across the period or across the group, like that. Down the group ionization energy decreases due to increase in size, okay. Now across the period increases. Why increases? Due to decrease in atomic size, okay. And there are some factors to be discussed across the period. What are that? There are the factors affecting, like electronic configuration, okay. So how this electronic configuration affects? So you will be seeing highest, like greater ionization energy in case of full-filled electronic configuration, half-filled electronic configuration, something like stable electronic configuration right now. So tell me, what is the order we got for second period elements? What are the second period elements? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Tell me. So this is full-filled electronic configuration, so highest one. Between these two, fluorine is electronegative, having more, okay. Between nitrogen and oxygen, here it is 2p3, 2s2, 2p3, this is 2p4, okay. So removal of electron from nitrogen is difficult as it is having half-filled electronic configuration, okay. Therefore nitrogen is having more electron ionization energy than the oxygen. So between carbon and nitrogen, between boron and carbon, between beryllium and boron, beryllium. Why beryllium? So it is having 2s2 electronic configuration. This is 2s2 to p1. So removal of electron from this p orbital is easy when we compare with this s orbital, because s orbital is more close to the nucleus. Okay, if it is more close to the nucleus, electrons in that orbital will be strongly bound to the nucleus. So in order to remove that electron requires high energy. Therefore the ionization energy of beryllium second group elements is greater than this 13th group or third group here, 3a group. Okay, so beryllium is more than boron. So this concept is called here, and this effect is called penetrating capacity of s orbital is more, s orbital electrons are more than the p orbital. Next, between this beryllium is more. So now what is the finalized order for this? So least is for lithium, then next boron, next is beryllium, next is carbon, oxygen, nitrogen, fluorine, neon. Yes. Okay. So now based on this, I just wanted to ask a question for third group elements. Tell me, third period elements. Arrange them. What are the elements we have? Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. So arrange them. Whatever you have followed here, just do the same. Argon, chlorine. What you have seen the scenario here? Nitrogen, phosphorus, nitrogen, same group. So phosphorus more than sulfur. Next. That's it. So arrange the same like that. Okay. So what is the finalized order? You will get argon, maximum, chlorine, next phosphorus, sulfur, silicon, magnesium, and least is sodium. This will be your order. Is that clear? Yeah. Done with this. Now for a particular atom, now this is very important application. Listen here carefully. For a particular atom, atom A I have, it has 2 valency electrons. How many valency electrons are there? 2. Remaining electrons are inner electrons. So during chemical reactions, what we know, only valency electrons will participate. Okay, inner electrons won't. Okay, so now removal of these valency electrons only takes place during the ionization energy. It means we can remove inner electrons also, but it requires high amount of energy because it is very difficult. But valency electrons relatively easy to remove right now. So now you will be seeing for the first electron you can easily remove, for second electron also little bit easy only, but third electron will be very difficult. Why? Because that electron, the third electron present in the inner core electrons, those are inner core. Okay, so the removal of those electrons is highly difficult. Okay, it requires highest energy. It means first 2 valency electrons are easy now. It means first 2 ionization energies are relatively near to each other, but third one will be having a large difference when we compare with the first 2 ionization energies. Okay, now if I have 3 valency electrons, what is the story you can say? First 3 ionization energies are relatively near to each other, but fourth will be very large one. There will be greater difference between the first 3 ionization energy and fourth one. Okay, if I have 4 valency electrons, same story here. After 4 electrons, sudden jump will be seen in the ionization energy. Greater large jump will be seen. Okay, is that clear? Now with this explanation, I want an answer for this question. Yeah, so answer fast. See, successive ionization energies are given for 1, 2, 3, 4, 5 are given. But where you are seeing sudden jump in the value? 4th one or 3rd one or where? 4th one. See 800 like almost 3 times and 800 almost 4 times, like that we have. But here if you see, this is 2000, 3000 we have, this is 25,000. So which is a huge jump right now. That is jump is after 3 electrons. So how many valency electrons are there in that atom? 3. Now identify the element having 3 valency electrons in the 4 options. Boron is having 2s2, 2p, 1 as a valence electrons. This is having 2s2, 2p, 2. So 4 valency here, 3 valency here. So option 1 is perfect. If you see for this, you have 4. Okay, how many? See here, you have this 4 now. Here you have 2s2, 2p, 4. So 6 valency electrons here, and this is having 5 valence. So which is the perfect answer? Is that clear? Right. Okay, next tell me for this.
Option 4.
Yes. Next, arrange this. Huh?
Option 4.
So just tell me C,
4.
max, D or
1.
this one? Like this now?
Yes.
Yeah. So which option it is?
4.
Yeah. Yesterday I think we did this. Yeah. Tell me for, okay, important points here. So what is the important points we need to mention here? Ionization energy increases with decrease in the size. Okay. So if small size, more ionization energy, large size, less ionization energy. Okay. Increases with decrease in size. And for or an ion, energy like ionization energy increases with decrease in the screening effect. What is the screening effect? See, screening effect means, just now I told you, nucleus, these are the shells we have in which electrons are present. Okay. So now here I have a valency electron. Okay, this is the electron that we need to remove here. That is what ionization energy. Now along with that, we have some electrons this in the inside also now. If these inner electrons are shielding this electron from the nuclear force, see, if there is no electrons here, this nucleus strongly bind this outer electron, yes or no? Yes. Because opposite charges. Yes. Okay, but if we have more inner electrons here, or they are shielding the nuclear forces on this electron. Shielding means what? They are like a wall here. Okay, therefore due to this, what happens? The nuclear force on this valence electron less. Therefore what happens? I can say if more shielding effect is there and more screening is there, electron can be easily removed out. Why? Nuclear forces are lesser, therefore easily removed. So what is the statement I have mentioned here? See, ionization energy increases with decrease in screening effect. If screening effect increases, ionization energy decreases. Okay, is that clear? Okay. So now next, one more concept I told you, penetrating power of orbitals. Which orbital is having more? I told you s orbital. That is the reason beryllium boron is having different scenarios. Beryllium is more because s orbital electron it is. This is p. So removal of s is difficult. Okay, discuss it now. Yeah. So now if you study one more thing, ionization energy left to right in the periodic table, what happens? Increases. So it increases like this in a period. Down the group decreases. Increases, decreases, you are saying. If I go like diagonally like this, no change. See, increases, decreases. See, increases, decreases. The net resultant will be almost 0 right now. So the elements which are diagonally placed will be having almost similar ionization energies. Like any elements, like what are the elements here we have? First lithium, beryllium we have now. So beryllium, after this magnesium. See, lithium, beryllium are lithium, magnesium are diagonally placed elements like that. Okay, next. So what are the applications of ionization energy? See, metals are electropositive, we are saying. Electropositive means they will be having tendency to release the electron easy now. Okay, they have low ionization energy. See, applications of ionization potential or ionization energy. See, metals and non-metallic character. So metals have low ionization energy. Can I say why? Metals have tendency to lose the electron right now. So it requires less energy to pick out one electron. So more like low ionization potential or low ionization energy indicates they have more metallic character, and high ionization energy indicates they are non-metals like fluorine, chlorine, etc. Okay, so this is about the one thing. Next we have reducing character. Similar to lower ionization energy, they have more reducing. So now which metal is more reducing? If I give different metals like cesium I am giving, rubidium I am giving. Which, like, tell me group elements, first group elements like lithium, sodium, potassium, rubidium, cesium. Now I have given these two elements. Now tell me which element loses electron easily? Down the group ionization energy decreases. Cesium loses electron easily, so it releases electron easily. So low ionization energy for cesium, so it has more reducing character. So just remove this lithium, do not compare lithium here. So in these options, which is strong reducing agent? Which is a strong reducing agent? Cesium. Why? Why? It has lower ionization energy, so it can easily give the electron to other species, they get reduced. Okay, so they are getting reduced now, so I can say this is having more reducing power. Who is having reducing power? Cesium. Next rubidium. Next potassium. Least is sodium. Okay, so now I have removed lithium from here right now. So actually lithium should be least now, but one more factor is there in order to understand reducing character, that is called hydration energy. Okay, not included here. So considering both, that lithium exceptionally comes first. Okay, it has to be least but coming. So this is the order. First study about this and lithium put here. That's it. Is that clear? Yeah. Next. First A group elements have minimum ionization potential. So they are strong agents. Okay, so like this. Okay, lithium, what I told you, you should keep it exceptionally here. Okay, so otherwise you just study other than lithium. Okay, so why I am saying lithium to be having maximum? Exceptionally it is having more hydration energy. Okay, next. See, 7th A group elements means halogens have maximum ionization potential, so they are strong oxidizing agent. If low ionization potential, strong reducing agents. High ionization potential, strong oxidizing agents. Okay, is that clear? Write that note, that points. Okay, low ionization energy, strong reducing agents. High ionization energy, strong oxidizing agents. Okay, and the next, here we have electron gain enthalpy. Okay, this is also important property to be discussed. Yeah, so what does it mean? See, when an electron is added to neutral gaseous isolated atom, converts into what form? Negative form, anionic form. So if X is an atom, now we are adding an electron to this. This atom is in gaseous form, which is an isolated atom. Now when we add this electron to it, the enthalpy change accompanying the process is defined as gain enthalpy. So during this process, conversion takes place something like this, anion formed, uni-negative anion. So now what is this process? The energy gain, the electron gain. So during this process, energy may released or absorbed. That whatever the energy change is there, we are calling it as electron gain enthalpy. Okay, yeah. So most of the cases, electron gain enthalpy will be here, it will be negative. So what do we mean by negative here? More negative value means it has more tendency to gain the electron. Okay, yeah. So here electron gain enthalpy provides a measure of ease with which electron added to the atom to form anion. Okay, so this is IE, like electron gain enthalpy okay, first one. If I add one more electron, it will be 2. So this can be positive or it can be a negative value, but this second one will be always positive value. You will always get a positive value. Why? Because see, already it is a negative charge right now. To that, if I add one more electron, what happens? Between this electron and between the negative charge, negative and electric repulsions are taking place now. So it is very difficult to add the electron to the anion. Therefore, it is always positive. Okay, remember that line. Okay, next let us move forward. So what are the factors affecting here? Atomic size. Okay, so smaller atomic size, easily it can take the electron because nuclear forces are more, it will take the electron readily. Okay, like that. Next, effective. See, down the group size, what happens to the size? Decreases. So gaining a tendency to gain the electron. Read the statement. Electron gain enthalpy is inversely proportional to the atomic size. So see, just listen. I have small atom, large atom. Who will gain the electron easily? Small atom. Why small atom? Means it has more nuclear charge now. The tendency to attract that electron will be more. Okay, so the tendency of gaining electron will be more for smaller atoms. Okay, yeah. So down the group, tendency to gain the electron decreases. Okay, right. This is, remember here. Next, effective nuclear charge. It means more positive charge, they can easily gain the tendency to gain the electron will be more for higher nuclear charge containing species. Okay, higher the effective nuclear charge, higher will be the negative electron gain enthalpy. What is this negative gain enthalpy? It means more tendency to gaining the electron. Okay, it means more amount of energy is released during that process. If more energy released, tendency to gaining the electron. Okay, next, screening effect means higher the screening effect, lower will be the effective nuclear charge, so it has less tendency to gain the electron. Okay, and electronic configuration, half filled and fully filled electronic configurations are already stable. Addition of electron to that will be difficult now because they are already stable. Now by adding electron it becomes unstable. Okay, by adding electron becomes what? Unstable. Therefore they won't take that electron easily. So addition of electron to that system is difficult. So electron gain enthalpy either 0 or positive. It means it is becoming difficult to add. If it is negative, you can say easy to add. Okay, yes. Next here, see, we can also have one more term, electron affinity. Okay, so same terms here, like saying the same tendency to gaining the electron only. See, if I look down the group, these elements, how they are? Electron gain enthalpy, you just check the values, minus 349, minus 324. So which is having more tendency to gain the electron? Tendency to gain the electron, which is releasing highest energy, minus with that sign you with like that magnitude you tell me which is bigger magnitude here, value is big for chlorine right now. So it has more tendency to gain the electron. Okay, yeah, down the group tendency to gaining the electron decreases. Who is having maximum? Chlorine, if I consider halogens. Okay, so you should say why not fluorine now? Fluorine should have maximum, but chlorine is having maximum. Why? Because fluorine and chlorine, okay, not hydration, but their sizes. So tell me who is having bigger size? Chlorine or fluorine? Down the group size increases now. Okay, chlorine. Okay, what is the electronic configuration for these 2s2, 2p5, and this is 3s2, p5. Okay, after 3p we can also have a 3d0. Here we do not have anything like a 2d, there is no 2d. Okay, now if I add one electron to this chlorine, it becomes chloride ion. If I add one electron, it becomes fluoride ion. This extra electron goes to this p orbital, right? Now p6 it becomes. Here it can also take this extra electron. Now see, this chlorine atom has some space to accommodate this incoming electron, either in P or in D. Some space is there, but that kind of space do we have in the case of fluorine? No. So after accepting the electron, there will be repulsions between the electrons of the fluorine. Due to that reason, relatively fluorine is having less tendency than the chlorine. Is that clear? Okay. Always remember, third period elements are having more tendency to than the second period elements. See, third period element is chlorine, then second period element is fluorine. Which is having more? Chlorine. Again, sulfur, oxygen. Sulfur. Okay. Will you remember that? Yes. Carbon, silicon. Okay, like that. Okay. See, boron, aluminium. Is that clear? Okay. Now, what is the resultant order for 17th group elements? Halogens, you tell me. Fast. Chlorine, fluorine, chlorine, fluorine, bromine, iodine, and astatine. Okay, like that. Is that clear? Now, oxygen family, you tell me. Sulfur. Here oxygen is exceptionally weak here. So exceptionally less for oxygen. So keep it the oxygen at the last. Okay, sulfur, selenium, tellurium, polonium, like this. Like this. Exceptionally less, see, oxygen due to small size. Okay, next. Is that clear? Like this, they may ask for any of the group elements or period elements. You need to ready to answer. Okay, is that clear? Yeah. See, if you observe, like noble gases are stable now, so adding the electron to them will be difficult. Okay, that's why they have positive values. Check here.
Yes.
Right now, again, even the second period elements, see how their values are? Positive values now. So positive values means it is difficult to add the electron. Okay, so again, nitrogen having half filled configuration now. So it is also having positive. They have very weak tendency to gain the electron. Okay, is that clear?
Yes.
Right. That is also same story applicable, same. Okay, but values will differ. That's it. Next, tell me absolute values of electron gain enthalpies of the halogens. Which is the correct option? Tell me. Which option will be correct here? Chlorine, fluorine, bromine, iodine. So fourth option we discussed. Next, oxygen family also discussed. Tell me. Sulfur, selenium, tellurium, polonium, oxygen. Okay, next. Electronegativity. So how can you define this? See, electronegativity means it's a measure of tendency of an element to attract the bonded pair of electrons in a covalently bonded molecule towards itself. It means just easy. Here, look at here. I have atom A, B, which are bonded by a covalent bond. Okay, which are connected by a covalent bond. Now, the element which have tendency to attract the bonded pair electrons towards itself is called its electronegativity. More the electronegative atom, more is the tendency to attract the bonded electrons towards itself. The covalent bond is dragging towards boron, like atom B here. So I can say that B element is having more electronegativity than the A. Okay, so electronegativity of B is greater than electronegativity of A. So due to this reason, what happens? There will be partial charges created here. See, tell me which element will be having positive here? See, this fellow is losing electron, which is polarizing towards B now. So this should get a negative charge, this should get a positive. Is that clear? The taking species should get a negative charge. Electron density is moving towards B. So B should get a partial negative, like that. Okay. Due to the electronegativity difference, polarities are created. Our bond can be considered as polar bond. It's a covalent bond only, but I can say polar covalent. Okay, I can say polar covalent, polar non-covalent. But due to electronegativity difference, bond formed is polar covalent bond. If I have a bond between A and A, what is this bond now? Non-polar but covalent. By because atom both have same electronegativities now, it cannot be polarized, so non-polar. Clear? Yeah. Next, what are the factors affecting on electronegativity? Size. Again size. Okay, so electronegativity is inversely proportional to size. Small size, more nuclear charge, attract the bonded electrons towards itself, so more electronegative. Okay, so size inversely proportional to electronegativity. Okay, next, nuclear charge. More is a nuclear charge, it means more is a positive charge, it can attack the electrons. No? Negative charge means electrons only here. So more nuclear charge, more positive charge attract the negative electrons easily. Okay, so it means electronegativity is directly proportional to the effective nuclear charge. Okay, nuclear charge directly proportional, or electronegativity directly proportional to nuclear charge. Okay, hybridization again. Next, more is the s character, more is the electronegativity. Why? Because s orbital is more close to the nucleus. So if nucleus is more closer, so what happens? Positive charge is more, bonded electrons are dragged more. So more s character, more is the electronegativity. That's why here 50% s character and 50% p character in sp hybridization. Next, here you just divide 100 by 3, 33.33 and 66.67. Okay, like that. Okay, next here this is 25% like that. 25 and 75 for P. Okay, is that clear? Next. Arrange the given elements in the basic based on their electronegativity order means how, what's your simple order? Remember, in this table, in complete periodic table, the highest electronegative element is fluorine, second most is oxygen. Now look at this table before answering this, so that you will get more clarity. Yeah. So here we have Pauling scale of electronegativities. We have two scales actually, Millikan scale, Pauling scale. Okay, yeah. So see, fluorine is having 4.0. Okay, after that 3.5. Oxygen is 3.5. See, nitrogen and chlorine almost the same. Okay, so in the complete table, if they ask what is the highest electronegative element, fluorine. Okay, now what is the least electronegative or most electropositive? See, if an element is least electronegative, that can be highly electropositive, because terms are different, opposite now. So electropositive elements lies this side. So where it is exactly? In this you see electronegativity value is least for this cesium. Okay, francium is there, that is radioactive, but normal element means you should say cesium. Okay, so cesium is least electronegative or most electropositive, and this is most electronegative. Okay, clear. The bond, the compound formed from the cesium and fluorine is highly ionic. So cesium fluoride I can write. Cesium fluoride. This is the strong ionic compound formed. Okay, because electronegativity difference is more, so that will be more ionic in nature. Okay, clear? Yeah. So now in the exam, they will be also asking questions based on their electronegativity values. So try to remember the elements having electronegativities, like see boron 2.0, how it is varying 1.5, 1.6, 1.7, like that. Try to remember for few elements like p block and s block elements especially. Okay, like phosphorus, sulfur 2.1, 2.5. Okay, and carbon is 2.1 and hydrogen is 2.1, carbon is 2.5. Which is more electronegative than between carbon and hydrogen? Carbon. Remember those things. Yeah. Over up to here? Yeah. So try to answer this question now. First, fast. Huh? Which is more electronegative?
Chlorine.
Next? Oxygen. This one? Yeah. Next, let us move forward with few more examples. Here one more thing I need to tell you. What is the applications of this electronegativity? So we can decide whether a given compound, especially oxides, whether they are basic oxides, acidic oxides or amphoteric oxides. Okay. So now nature of oxides can be decided looking at their electronegativity difference. If electronegativity difference between atom and that oxygen atom, the central atom, I am saying oxides, definitely it should contain oxygen. So electronegativity difference between that atom and oxygen, if greater than 2.3, so I can say that is generally the examples here comes is alkali metal oxides, alkaline earth metal oxide like sodium oxide, potassium oxide, superoxides. Okay, oxides are basic. This metal oxides, alkali metal oxides are basic in nature. Okay, and remember this, even second group elements are there now, magnesium, calcium, strontium, their oxides are also basic except one. So beryllium is there now, beryllium oxide is amphoteric, remember this. Okay. Okay. Next, if electronegativity difference is almost equals to 2.3, then we can say amphoteric. If electronegativity is difference less than 2.3, should say acidic, greater than basic, less than acidic, equal amphoteric. Okay. So now along the period, what happens to the electronegativity? Increases. Electronegativity increases means acidic nature, see between oxygen and the element attached, electronegativity difference will be decreases, so acidic nature increases. Okay, so decreases, acidic nature increases like this. Okay, so down the group basic nature of oxides increases, across the period acidic nature of oxides increases. Remember, P block elements oxides are acidic in nature, like general words these are. S block elements oxides are basic in nature, exception I told you, beryllium oxide. Okay, yeah. So down the group basic nature of oxides increases. Okay, down the group acidic nature of oxides decreases. Okay, why? Electronegativity decreases down the group, so their acidic nature also decreases. Okay, you got these statements now. Now try to answer these questions. Just wait, I will show you some questions. Just make a question, HNO3, otherwise oxides I am saying now, so take oxides first, then we will come to acids. N2O3, P2O3, AS2O3. So tell me which is strong acidic oxide, or tell me their acidic oxide nature, which is more stronger. So which is why N2O3? Its electronegativity is more. So down the group electronegativity decreases now. So N2O3 is more acidic, then P2O3, then H2O3. Is that clear? So next, if oxide is having same oxidation like same element, central atom is same. I am saying N2O3 and N2O5. Both are having same central atom now. Which is more acidic? Electronegativity is same means you check for their oxidation state. Oxidation state of nitrogen is +5 here, this is +3. Okay, more oxidation state increases. What I can say? See, what is the factors I told you? Size. Next what? Small size, more electronegativity I told you. After that, nuclear charge. See, more positive charge means more nuclear charge na. So more nuclear charge, more is the, so oxidation state increases, so acidity also. Why? Because nuclear charge increases, becomes more electronegative compound, so acidic nature also increases. Clear na? Yes. Right. Try this question. What is your answer for this? Which are the following options correct order of arrangement? Following does not agree with the variation of property which is mentioned in the bracket. So electron gain enthalpy, is this correct? Which is more? Fluorine or chlorine? What is the order of electron gain enthalpy we discussed? Chlorine is greater than fluorine. So, but here this is wrong. So, first option is not correct. Okay, next check for other options also. Increasing metallic radius. Down the group, what happens to the size? So, this is correct. Next, this one. Increasing ionic size. What happens to the size? F minus Na plus, so more negative charge, more is the size. Okay, small positive charge, more positive charge. As positive charge increases, size decreases. So this is also correct. Next, this one. Increasing first ionization in enthalpy. So which is having first ionization enthalpy greater? Greater first ionization enthalpy between, these are second period elements now, tell me. Tell me what are the second period elements? Lithium, beryllium, tell me that. Which is having maximum? After that?
Chlorine.
After that?
Nitrogen.
Nitrogen. After that? But what they mentioned? Is that correct? No. So this is also incorrect. So I can go with 1 and 4 for this particular question. Okay, because whether maybe it is printing mistake here or somewhere else, fourth option is definitely incorrect. Okay, after that first one. Okay, most incorrect one will be definitely fourth one. Okay, next. You need to arrange, or you need to arrange like select the pair which is having acidic in nature oxides. So now calcium, what is this calcium? Second group element now. So alkaline earth metals forms basic oxides or acidic oxides?
Basic.
So this is basic oxide. So they are saying pair of acidic oxide. So this is basic oxide. Here also we have calcium, basic oxide. Okay, what about barium? Which group element? Beryllium, magnesium, calcium, strontium, barium. that is also belongs to second group element, S block. So that is also basic oxide. So we have basic oxides in this. Simply you can go with the third option, because boric oxide, okay, silicon dioxide, okay, both are boric anhydride, this is, both are acidic. Okay, next, try to match this. Hydroxides are given. So this, if I have basic oxide, if I hydrolyze that, we will get bases. If I have Na2O, what is this? Means what? Sodium oxide, basic oxide. Now, if I hydrolyze that, we are going to get a NaOH, sodium hydroxide, 2 moles. So it's a base now? Yeah. So now, similarly, if I have acidic oxide, let us say I have CO2, carbon dioxide is an acidic oxide. If I add water to this, we will get a H2CO3, carbonic acid. Okay, if I have nitric acid, nitric oxide like N2O5, we discussed N2O5, this is acidic oxide. Upon hydrolysis gives HNO3, nitric acid, like acidic oxide gives acids, okay, oxo acid, okay, yeah. So now tell me, NaOH is base or acid? Basic. Next, BeOH twice. What I told you, beryllium oxide, amphoteric. So this one also be amphoteric. Okay, next, calcium hydroxide, basic. Okay, next, this is, if I told you B2O3 is acid, respect to hydroxide will be acidic. Okay, Al2O3 is amphoteric. Okay, next. So based on this, you can match here. Which option will be suitable for that? You just look here and match it. Okay. So next, A2. Okay, A2 here we have A2, B3, A2, B3, only fourth option. That's it, correct. Next, given below are the oxides, among them is amphoteric. Okay, it means amphoteric means what? It can show both acidic nature, basic nature. If I treat that oxide with acids, it will act as a base. If I treat it with base, it will act as an acid, like that. Okay, yeah. Next, anomalous pairs. See, anomalous pairs means like, see here, some elements of second period elements, some elements of second period elements, some elements of second period shows similarities in the properties with the third period elements. Why? Because I told you, like lithium, magnesium, which are diagonally placed, will be having similar ionization energies. We discussed now. So due to that reason here, the elements which are diagonally placed, their compounds will show similar properties. Okay. For example, lithium, magnesium, I have mentioned here now. Here we have beryllium. Okay. After this, what we have? Boron family. Okay. Boron. After that, what we have? Aluminium. Here we have. Okay. So if I say beryllium carbides and aluminium carbides, if I take, if I hydrolyze, then we will get methane as a gas. Both will give methane gas. Okay. So this kind of similarity, see, examples, what are the elements? Here we have lithium resembles with the magnesium, just remember this. Okay. Beryllium resembles with the aluminium, just there I have mentioned. Okay. Like this, you just remember this. Okay. So what is the reason for anomalous behavior if they ask? Due to small size, large charge to size ratio or radius ratio, they can say. Okay, yeah, and high electronegativity of elements. Okay, like this. So what are the elements? Like lithium, magnesium, beryllium, aluminium, boron, silica. Okay, this is about the diagonal relationship or elements having diagonal relationship. Now you just give a practice from your side, practice some questions of our module. Okay, if anything is remaining, we'll discuss in the next class. Okay, yeah. So I will be checking your notes tomorrow, whatever you practice. Okay. Thank you.